Okay, so I was silly yesterday. I found a more 2025 way of sharing the link. So I suggest you just put it on your smartphone, the PDF, and in case you want to leave back, you can, right? So has everybody had a chance to get it? Otherwise, it will disappear for good. Okay, so yesterday, I stopped introducing log-smooth morphisms. Let me just remind you what that was. So we had these log morphisms, we had log structures, that was this sheaf of monoids. Let me maybe quickly remind you of that thing. So it was a homomorphism of sheaf of monoids. I think of mx always as being multiplicative, although once I go to m bar, I divide out the invertible functions, I think of it additively. Okay, so because that's how it naturally arises in, let's say, toric geometry. And then we have the OX multiplicative, so it's just some morphism, and it's such that the invertible functions map isomorphically. And the most important example is, of course, pullback from toric geometries, where you again can think of invertible functions, regular function at invertible outside the toric divisor. Okay, so and then we have a notion of log morphism, and these are just come up, and the most important notion is of a log-smooth morphism. So these look locally torically. So this means we have a chart. We have charts for x and y that are compatible with the map, with this map, in the sense that this diagram commutes. So charts just mean that these morphisms are strict. If you remember, that meant that if you pull back this m bar sheaf, it induces an isomorphism. Okay, so here are some examples. If you take the trivial case where, it's not a trivial case. The case where the log structure on y is trivial, meaning it's only invertible functions. So m bar is identically 0. So this translates into q equals 0. Then this means that x is toroidal. So there is this, how do we get the divisor d? So a toroidal pair, remember there was a pair of a variety with a divisor that locally looks like a toric variety with its toric divisor. So how do we get the divisor here? It's just the support of m bar. Okay, wherever the log structure is non-trivial, that's a point of d. So that gives a pair x comma d, and which is locally, by the definition, right? It's locally isomorphic to that thing. Sorry, I forgot something very important. This map is not only, that's just a chart for the log structure, but to make it a log-smooth morphism, this morphism must be smooth. Okay? So that's I forgot the most important part of the definition here in copying my notes. Okay, so then let's reproduce normal crossings degenerations from that notion. If you take for q n, the natural numbers, and for p n to r, and take for this homomorphism the diagonal map, then you translate it into a morphism of rings. It means you map T to the product x1 to xn, or r, or whatever you have. And then your x is smooth over this, so it's a product with something smooth. That's a normal crossing degeneration. Well, assuming that y is smooth, otherwise you get some base change of some normal crossing degeneration. And then the coolest thing of this is, now you can restrict the whole stuff. Let's say you have a normal crossing degeneration. So logarithmically it looks like this. You can restrict it to the central fiber. Now the central fiber of a normal crossing degeneration is a union of smooth varieties that meet normal crossings, okay, in normal crossings divisors, but it's reducible. And so you can look at this whole picture. Let's say x lives over a smooth curve S. You have a special point 0, and the divisor d is your central fiber. So you have a pair x comma d giving you a log structure, and a pair s comma 0 giving another log structure, and a morphism from a log morphism from x to s with these log structures. So that's that. And then I do a fiber diagram. So I take a base change to this point 0 that will produce a standard log point here, as we saw yesterday. And then some log space that is log smooth over this guy. I didn't say this, but log smoothness is stable under base change. It's almost immediate from the definition. So now you see what this is, right? So you have this map, this kind of interesting log space over a standard log point that's log smooth. So the slogan is, a log space that is log smooth over a standard log point looks like the central fiber of a normal crossings degeneration, if the corresponding map of log structures is locally of this form. Okay? So let's do an explicit example. Let's see some equations. Let's take the homogeneous degree 4 polynomial to get a degeneration of K3 surfaces. Okay, so I write down this kind of degeneration of K3 surfaces, t times f plus z0 dot 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 z3 equals 0. So that gives a hypersurface in P3 cross A1, threefold, that fibers in surfaces over A1. And the general fiber is obviously the zero locus of a quartic, of a degree 4 polynomial. That's a quartic, so that's a K3 surface. And the center fiber, so you say take t equals 0, you just get the union of hyperplanes. Sorry, what is that? What is that? That should be P2, obviously. Okay, so now we have a union of hyperplanes that just a union of coordinate hyperplanes, so that forms like a tetrahedron-shaped union of hyperplanes. And that's almost a normal crossings degeneration, not quite. The reason is that x prime is still singular. You see these, it has 24, if f is general, okay, then it has 24 A1 singularities. These are at the points of intersection of the singular locus of the center fiber. So that's a union of 6 lines, 6 P1s. And on each line, you have the zero locus of degree 4 polynomial, that's 4 points. 6 times 4 is 24. So you have 24 A1 singularities. I've tried to draw this here, right? So x0 prime looks just these 6 copies of P2, sorry, 4 copies of P2. But then looking in the total space, you have this location of the 24 A1 singularities. You can now blow up the irreducible components of the central fiber in the total space. That's not a Cartier divisor. That's why it does something to produce these small resolutions. So that replaces each of these points with a P1. And depending on how you choose your blow up, the P1s end on one or the other component. So this looks like this. And then it's normal crossings. Okay, so you have to resolve the A1 singularities by blowing up one of the irreducible components. And then the total space is smooth. You get a simple normal crossings degeneration x over this curve S, which is just S1 in this case. And the central fiber is this log smooth guy, right? So this thing here has a log smooth structure over the standard log point. Okay, so I'm telling this because I'm giving this example because this is an example that shows you the kind of maybe the power of log geometry that is probably totally hidden until you have seen it before at this point. So the story goes as follows. So Bob Friedman in his thesis 1983 developed a theory. So he looked at the problem that if you have these kind of normal crossing spaces like the union of 4 hyperplanes, when can you smooth it? Or is the union of 4 hyperplanes blown up in 24 points? So when can you smooth this? And he noticed there is an obstruction in smoothability that sits in this sheaf. I'll explain this in a second. So he calls this the vanishing of this obstruction that x0 is d-semistable. So that's a notion that's intrinsic to x0. It doesn't depend on anything else. So d-semistability, according to Friedman, means you look at this x sheaf. So if you stare at this, so it's a sheaf of omega 1 x0 O x0. As long as omega 1 x0 is locally free, this vanishes. So where is it not locally free? At the double locus. So the double locus is the union of these 6 P1s. And then it's an easy local computation that shows you that it's a locally free sheaf on this double locus. Okay, always. So if you have a normal crossing surface, you get this line bundle for free. D-semi-stability, so you get an element of the pick x0 thing. In this case, it's a genus 3 curve. So this is non-trivial, okay? And D-semi-stability means this should be non-trivial. Should be a trivial sheaf, sorry. X1, this should be a trivial sheaf. And so if you change, so how can it be non-trivial? So in Friedman's papers, he actually computes that if you take out this last bit, so you take out one of the irreducible components, the X1 sheaf is always trivial. And then depending on how you glue the last bit in, it changes the isomorphism class of this sheaf. And only very particular gluings, a discrete, maybe it's unique in this case, I forgot, a discrete set of gluings make it D-semi-stable. Okay, so no log geometry here in 1983. But in 1994, Kawamata and Namikawa observed that a D-semi-stability is actually equivalent to having a log-smooth structure over the standard log point. Okay, so of a particular form. So the statement is, you take a normal crossings variety, it is D-semi-stable if and only if there exists a log structure on x0 and a log-smooth map to the standard log point that locally looks like this diagonal map we had before that we could call like a normal crossings or central fiber of a semi-stable degeneration. And then it's actually easy to produce, it's actually, I shouldn't say easy, it's not totally trivial, you have to prove a slight bias change theorem and so on, but it's kind of easy. Certainly much easier than what's in Friedman's thesis to reprove Friedman's theorem. Namely, if you have a D-semi-stable K3 surface, actually that's an equivalence. And the way I stated it's an equivalence. If and only if it is smoothable with a smooth total space. So be careful, the total space could not be smooth, then this is not an equivalence, okay? But if you insist on the total space to be smooth, then this is an equivalence. And you can reprove this simply because there's some logarithmic deformation theory and the obstruction group just vanishes for kind of trivial reasons. I should remark that this is special to dimension 2, and higher dimension is a lot more subtle. And some of what I did with Mark Rose in my program on mirror symmetry gave kind of sufficient conditions how to, or produced explicitly such smoothings in higher dimensions. And I also want to mention more recent work of Felten, Philip, and Rodat, who looked at this from a non-mirror symmetry perspective, just looking into log geometry and so on, doing deformation theory. Okay, so and that's the last few lines of this slide. This morphism is not, oops. If you're intimidated by saying what this morphism, or let's say, maybe I should say x0, mx0, okay, mx0, which actually defines this kind of log morphism, right? So we have a log structure here. Where is it? We have a log structure here on x0, but then we also want a morphism to the standard log point. To give this morphism is very easy. It's just the same as giving a section of your log sheaf. Okay, simply by putting this, you remember there was this map, this F flat, the kind of enrichment, the log enrichment of the schematic map. And it would just map this point 1, the unique generator of this n, of the log structure here, to your row. And that defines the morphism. Okay, so that's not a big deal. Any questions at this point? Okay, so then we'll move to kind of the second talk, or the second part of the slide. So we are moving to tropicalization. So I announced that once you have a log space, you get a kind of tropicalization for free that in situations when it applies, agrees with traditional notions of tropicalization. So what is the traditional notion of tropicalization? So if you open a book like McLagan-Sturmfeld's on tropical geometry or one of the early papers, you would find that they work over it's algebraic geometry over some complete value, algebraically closed valued C algebra, something like, for example, you could take Puiseux series that you could write like this, which is the algebraic closure of this ring of the field of formal power series, and then you look at a variety in k star to n. So very, very classically non-schematic, just the zero locus of some ideal in k z1 to plus minus 1, zn to plus minus 1. So that's a hypersurface in a torus. Sorry, not a hypersurface. It's some subvariety in this torus, this algebraic torus k star to n. The interesting thing is, and that's not algebraic geometry, that there's a valuation map from this k star to n to Rn. If you know Berkovich spaces, you will see, or non-Archimedean geometry, you will recognize this, but I'm not going to comment on that. And the tropicalization is still simply the image, the closure of the image of X under this valuation map. So this is one definition. There are two other characterizations that are sometimes useful and are instructive. So one is, if you like Gröbner bases and these kind of things, and it is a set of W in Rn. So Rn is a space of weights, W like weight. Once you have a weight, so a vector in Rn assigns weights to any monomial, right? So and then you can order your elements of the ideal according to this weights and finds this initial ideal, which is a kind of minimal or maybe maximal. I think it's a minimal in this case. Depends on some choices of signs. It's a minimal a set of generators here. So you takes the leading terms and takes the ideal generated by these. And the statement is, it's a set of weights such that the initial ideal is not invertible. Okay, it's not trivial. And well, I don't want to explain it too properly at this point. It's not so relevant. It's just an alternative definition. And you could also say there's a notion of trop I. So trop I interprets each polynomial in this ring by taking the valuation on its coefficient, okay? And then you get a polynomial in this kind of ring where the coefficient field is this max plus algebra, and it has a zero locus. So an element in here gives you a kind of piecewise linear function. And you look at the zero locus of that is where the function is not linear locally. And that gives a notion of tropicalization, or a zero locus of the tropicalization, and that all agrees. So this is something you find in standard textbooks. So what is this? From this point of view, it's kind of obvious, not from the other point of views, right? That this kind of thing, this tropical variety, is a cell complex. Yeah, so it has these piecewise linear pieces that are patched together. It happens, so if your variety was d-dimensional, pure d-dimensional, then actually your tropicalization will be pure d-dimensional, real d-dimensional, and so on, okay? There's one more maybe instructive thing if you're a more geometrically minded person like me. So if you look at the convergent case, So let's assume, so this is all formal here, right? But let's assume that your coefficients are actually holomorphic functions. So you actually talk about convergent power series, and so you get a family of subvarieties, xt, or analytic subspaces, xt and c star to n, for any sufficiently small t. And you take the limit for t to 0. And I probably got the sign wrong here. I guess I need a minus if I take t to 0. You take the image on what is called this amoeba map or log map. So this means you take the log absolute value of each of the entries to the base t. Maybe absolute value t, or t is real, okay? And that gives a certain map from c star to n or to Rn. Depending on t, you take the limit, and that actually happens to be also the tropicalization. And now I'm noticing I was inconsistent with my symbols. So what does it have to do with log geometry? So in log geometry, we start with a fine log space, and that gives us for each schematic point, if we work over a scheme, a monoid, right? Just a fiber of this sheaf M bar, the sheaf of monoids. So these were these toric monoids, these sigma dual intersected Z to N. So something very explicit. With trivial invertibles, so it's actually a kind of sharp integral points of a sharp cone. Now, schematically, we can look at points that are in the closure of other points. So let's take x in the closure of y, or y would be a generalization of x, or x is a specialization of y. Then there's a map of Starks from the deeper point to the more generic point. So this gives a map from px to py, a generalization map, just kind of restricting to some smaller set. So what is this generalization map? You take the pre-image of 0. So this is a monoid homomorphism. I have to be careful because we're so used to working with abelian groups and so on. But this is a monoid homomorphism, so we have to be careful by saying what the kernel is and so on. But let's just take the pre-image of 0. That turns out to be a face, just because we have a sharp cone on the image. Okay, there's a face of px. Complement is a monoid ideal. And the chi induces an isomorphism. I cannot divide out f. That doesn't really make sense in monoids. But what you can do is, first kind of extend your cone in the direction of f. So this is done here. You take px plus f group. So this is a cone that is kind of a ridge. And then you divide out, and you project along f group. So you divide out f group. And chi induces a map in this direction, and it actually is an isomorphism. So this generalization map is a projection along the face f. So if you think of some cones, some polyhedral cones somewhere, you take a face, and you just stare from this face and project down. That's what this map is. So this is good to have this intuition, or this picture in your mind. So I just wrote this here, yeah, projection along a face. What is this face? These are the exponents, now thinking of functions again, that become at functions, exponents at x, that become invertible at y. Okay? Being invertible means being divided by the ORX star, so that becomes 0 in py. So let's do this for A2, yeah, very concretely. So let's take x, the origin, y, the generic point of this z-axis. Then px is just n squared. So if you go here, if you go to y, what becomes invertible? All powers of z. So the phase is this lower boundary, and you project along this phase, you just become this ray, and indeed that's py. Okay, so this is not what we do in tropicalization. That's a dual side. So we have to dualize to get the tropicalization. The standard notation would be like this. So whenever you have a cone, you can form the dual, that's a Hom to R, larger or equal 0, as a monoid, and then takes the integral points. And now you dualize the chi. Now this becomes an inclusion of a phase. So dual to a projection along a phase is inclusion of the kind of perp phase. So F perp intersected sigma x is a phase in sigma x, and that is actually isomorphic, canonically isomorphic to sigma y. So we learned whenever you have a generalization, you get an inclusion of the dual monoids as a phase. So now once you have swallowed that, I can easily define what the tropicalization is. You get a bunch of, for each point, you get a cone. For each generalization, you get a phase inclusion in the other direction. And you can take the co-limit of this. Let's first be naive and take the co-limit as topological space, okay? Just as a first approximation. That works quite generally. So this is then a cone complex, as you would define maybe in algebraic topology, a little more generally, because it's not simply C's, it's some polyhedra, has some additional structure, and each cone is a rational polyhedral cone, so you know what integral points are. Let's do this for P1 cross P1. So this is a geometric picture. So you have stalks 0, n squared. You look at the corresponding cones. So each n squared gives you a quadrant. Each of the n's give you some half line, and the origin in the middle, the 0, sorry, in the middle gives you 1 point. And then here are all these phase inclusions, okay? And obviously, if you take the co-limit, you will just get this picture that you recognize if you know toric geometry as a fan of P1 cross P1. And that's quite a general phenomenon, okay? So I haven't talked about this, but many people in the room will know it. So to glue toric varieties globally, you don't just do one cone, but you have to match the cone, and that's done by the notion of fan. It just means you have a phase-fitting selection of cones in some vector space with underlying lattice. This is what I wrote n. Yeah, so if sigma is a fan, and you take the toric variety for this fan, then the construction of sigma is just sigma. It retrieves the fan as a set, together with its decomposition into cones, but you won't naturally have an embedding into a lattice or into a vector space. That has to do with the torus actions that you don't see logarithmically right away, okay? So it's just this cone complex, and so this gives you many examples of this kind of tropicalization. Look into books of tropical geometry, all kinds of beautiful pictures. All of these arise here very naturally. Are there questions? Okay. So the next thing you observe is, when you come from toric geometry, you might get the illusion that there is some kind of equivalence of categories or something. This is completely wrong. And it's good that it's wrong, okay? It's not disappointing. It's actually good that it's wrong. So let's look at an example. Let's modify this example a little bit. We take P1 cross P1, we blow it up non-torically in one point. That gives you some exceptional curve here. And you take the divisor, nevertheless, as a strict transform of your previous divisor. So that's still a union of 4 copies of P1. What has changed with the log geometry? It has changed, right? The space is different. But if you look at this sheaf M bar, nothing really has changed. You really still have the same set of points up to some trivial points that you've introduced along E. They have the same stalks, and the maps, the generalization maps are the same. It's exactly the same, okay? So this sigma x will be the same as the sigma of P1 cross P1. So doing the tropicalization is insensitive to operations that may change the geometry, they change the normal bundles and so on, but they don't change the kind of combinatorics of how you fit these strata together. So why is this good? We will see that these kind of tropicalizations are kind of the underlying, they determine they give the underlying space, or let me put it this way, they capture the possibilities of what can go on geometrically, but what does not have to go on, okay? So certain, let's say, stable log maps may look like they exist by looking at the tropical geometry, but then it depends on a particular geometry to decide which ones actually occur, okay? But having this kind of universal framework makes it a lot more useful because you can first solve a tropical problem, and that will solve the problem for a big class of geometries, and then look into the more refined things that have to do with Gromov-Witten theory and the virtual formalism and so on. So, and we will see something like this going on later in this series of talks. Okay, so sigma x only captures the combinatorics of the situation, not the finer analytic or algebraic geometries that we saw in this kind of D-semi-stability, for example, right? We'll never see this. Hence has a more fundamental and universal character. So the sigma P1 cross P1, yeah, when does it, yes, here's a question.
It's not adding E a choice?
Yeah, there was a choice, there are many other choices. Yeah, I can blow up any number. It will always give the same thing. So I'm just making.
Even if we put E, will we get the same cone complex?
Yes, unless you put it at the, unless you blow up this one of those zero-dimensional strata, right? Then you get another component, and it will change. Yeah, let me make this statement here. So when does sigma P1 cross P1 actually occur? It will occur whenever you have a normal crossing situation. Your space may be singular somewhere, but the log structure is important. So you would have these 4 divisors, or 4 whatever, okay, that have stock n, and they meet in something that has stock n squared, and the generalization maps are the projections. And you have some cyclic thing. Whenever this occurs, this is the only thing you need, then you get a sigma P1 cross P1, this kind of picture up here. Okay, so this is the information you capture. Okay, so now, at this point I said let's be naive first and talk about actual cone complexes. Life sometimes isn't quite as easy as we hope for, and unfortunately curves already have nodes that components that self-intersect, right? You look at the nodal cubic, that won't fit into what I described so far. So I have to talk about this a little bit. It's not super deep. It's very confusing when you think of it in the wrong way, so let me just tell you how the way you should think about it. The upshot will be we have to modify the notion of a cone complex very slightly, okay, and then you're good. So the problem is that cones can self-intersect. So we have these cones sigma x, and they can be automorphisms of the cone. If this mx bar is only locally constant rather than constant along a stratum of x. So what are these strata I'm talking about? So any logarithmic space comes with a stratification. So a stratum is a maximal locally closed subset, z and x, such that the restriction of m bar to the z is locally constant, okay? So particular rank stays constant. But as you can imagine, there can be twists. It's discrete because faces have to go to faces, rays have to go to rays, and there are only that many, finitely many automorphisms of a rational polyhedral cone. But you can have monodromy along a stratum. Let's look at one very confusing example that is also, which is kind of beautiful, that Dan Abramovich came up with as the Whitney umbrella. So we all know the classical Whitney umbrella. If you had some basic education in algebraic geometry, I think at some point you come across this beautiful singularity. So it's a zero locus of zx squared minus y squared. So the z would go in this direction. When you keep z fixed, you get this kind of union of 2 lines. And for z to 0, you would just get this double line down there that I couldn't draw very properly. I do remove this double line, okay? So let's remove the zero locus of z equals 0 because that's a little bad logarithmically. It's not a good point logarithmically. So this is then just the c star. This sits in c star squared cross c2 xy, so and that's my x. And the D is just the X is the ambient space, and the D is this kind of Whitney umbrella with this double line removed. This guy has a Z mod 2 cover. The D has a Z mod 2 cover, which is just a product of a union of coordinate lines in A2 cross C star. And the Z mod 2 action would what was it? It changes the sign of W and it flips U and V. So this is something that I wrote down here. That's a Z2 action. And you compute the invariant functions of this Z2 action. You find 4. You have your equation. This equation is given by U times V equals 0. So you want this kind of map to see that this Whitney umbrella is actually this guy, and I just wrote it down. You can check it at home. Okay? So it has this kind of twofold cover, unbranched cover. Sorry, it's not unbranched cover. It has this twofold cover, and obviously it's 2-to-1 along this double locus. Okay, so now what's happening if we apply? So this is a log-smooth space, right? It's a toroidal pair. It's not toroidal in the Zariski topology, but in the étale topology. Okay, you have to take an étale neighborhood, étale cover to actually unravel it and see that it's locally isomorphic to a toric variety with a divisor. But other than that, if you think like locally analytically, this is a perfectly normal crossings point anywhere here along this line, except that's the origin, but we removed that. Okay, so if you tropicalize, there's only one maximal cone, namely the sigma corresponding to this log stratum. That's an n squared. That gives you, an r larger or equal 0 squared. That's this guy. And the Z2 action just flips the cone. Yeah, so it just flips the 2 coordinates. That comes from the flipping of U and V here. So if you, geometrically, it's a C star. You go around, the two branches swap. Nothing you can do about it, right? But that means that in the tropicalization, you get this very weird thing, right? It's kind of a folded cone. And it really messes up your way of thinking of it. So the best way to deal with this, and I spent some time in convincing myself that there's really no better way to do it, is that the tropicalization of X really generally is only a generalized cone complex. That's a topological space. We still have a topological space, which in this case would be this half cone, okay? That, however, has the additional datum. It comes with an atlas that locally is given as a co-limit of a diagram of rational polyhedral cones. So that is a co-limit of a diagram, right? So you have a sigma, you have 2 arrows to itself, the identity and the flipping arrow, and you take the co-limit, and that's what it is. Up to equivalence of diagrams. Okay, so the tropicalization comes with a little more information that has to do with monodromy of the cones along the strata. Okay, that's all I will ever say about it. That obviously comes up if you talk about like domains of curves that have self-intersections, but other than that, we'll ignore it in the rest of my talk. Any questions to the tropicalization section? Does it make sense to talk about tropical compactifications? This has several meanings. So yes, it does. There's one tropical compactification that has to do with moduli spaces. That's probably not what you meant. Is that what you mean? So a moduli space, like algebraic geometric moduli spaces, and then you look at objects that kind of parameterize tropical whatever kind of things. The other thing is you can enlarge tropical varieties and go from cones to kind of completed cones. So you would add some geometry at infinity here. That makes sense, but we don't need it. The first one, yes. We are not there yet. So the tropical compactification you may be interested in is actually kind of what we will do with log geometry. Yeah. Okay, so let's look at log smooth curves. Yep.
Is there a way tropicalization
Is it tropicalization? Functorial, yes. Yes, very good question. It's kind of trivially functorial, right? If you think about it, we just kind of, we have this map of sheaves. I mean, the Stark functor is a functor, right? So, and then you dualize, it's functorial. So nothing can happen, right? It's kind of obvious that it's functorial. Yes. Okay, so log smooth curves. So these are the domains of stable log maps and log Gromov-Witten theory. So in ordinary Gromov-Witten theory, you have nodal curves. Now we upgrade it to log smooth curves. So we will insist that these are smooth over some base space. So we endow everything with log structures, but not any log structures. They have to be log smooth, and then kind of nodal curves come out together with marked points, come out automatically, as you will see. So let's look at how this comes about. Let's look at a normal crossings degeneration of smooth marked curves. So these things that you would get when you look at the Deligne-Mumford moduli space, or some, if you want to drop stability, and we have to drop stability for the domains to do Gromov-Witten theories, and you look at a stack of pre-stable curves, so just nodal curves, you pull back by some good maps, so you get these families. And let's say we were our one-dimensional base S. So let's say this is a curve S, and here you have an origin. I just call it 0. It's just some special point where the fiber becomes nodal. Okay, the other fibers are smooth. So maybe I assume the other fibers are smooth. Yeah, so obviously that's a toroidal pair, and it comes with a log structure as we did before, and it becomes a log smooth. You get a log smooth structure on this central fiber. So what does it look like? It has, so at general points, it just, sorry, what is the, sorry, I have to say this. So what's a divisor if we want to do this? We set the divisor D with this kind of central fiber, yeah? So this would be D equals C0, and the whole thing X equals C, okay? So this has a log structure, and the stalk of M bar is an N, just coming at a general point. It's just a smooth divisor here in this total space, so it just has one vanishing order that gives an N. That actually maps isomorphically to the N, or comes from the N giving from this kind of vanishing of the coordinate here, t equals 0, pulls back, so there's this N here. Maybe I should write this here too. So there's an N here, and that maps isomorphically to this N. So nothing interesting at these points. The morphism is strict there. Then there are two special points. So if we have marked points P, oh, sorry, I said this wrongly. It's not just C0. We also want these sections. How do I write these? Maybe I call them curly P, okay? Let's call them curly P. So, and then I have to take C0 union P. Okay, so there are two interesting points. Yeah, so so P, there's an N here, okay? And there's an N here. And at this point, there's an N squared. You know? This comes, one direction comes from this, the other one from that. And they're kind of independent, as you will see. It's a product situation. So this map here has nothing to do with that section, right? It only defines this equation. So this 1 maps to rho, and the rho at this point would just be 1, 0. Okay, that's kind of an easy point. The more interesting points, or most interesting points, are these nodes. As a node, we have seen we have this diagonal map, right? It's a normal crossing points 1 to 1, 1. Now this is N squared, so rho is 1, 1. This is what these kind of log smooth curves over the standard log point look like. We need a little more decorations, but let's, before getting to this, to get the correct definition in log geometry, let me emphasize these local models. So at a general point, we map t, z. Z would be the fiber coordinate to t. and the m bar C0 eta, it's the same as the m bar on the ambient space. Restriction doesn't do anything to m bar, okay? That's generated by this t factor, and that is an n, and the 1 in n just maps to this t. Then at a mark point, we had this additional z. So at a mark point p, I should say what this is. So this is the z equals 0 in my in these. Let's choose z equals 0 as the correct coordinate. Then the log structure up here at this point is generated by z and t corresponds to 1, 0, as we said. And at the nodal point, we have zw maps to z times w, and the log structure is generated by z and w, and the t corresponds to 1, 1. So these are the local models. So this was over, there was just some ad hoc thing over family of nodal curves. So what is the general picture? Let's say we work over log points, so spec q to c, and we want this to be log smooth, of course, fs, fine saturated, to get reasonable log structures that look like toric varieties. We want the fiber to be reduced, standard in talking about nodal curves. And then there's something slightly funny, which is called integrality, pi integral. So that involves, I mean, if your work C over point, that's flat, okay? There's nothing you can do. It will always be flat. But in logarithmic geometry, there is some kind of hidden flatness that you need to impose. Namely, if you have the local model, toric model, that CQ to CP that comes from the definition of log smoothness, these maps may not be flat. And integrality asks these maps also to be flat. And that just kind of forces it, together with the reducibility means that if you are over a standard log point, it will look like this. But integrality is something, if you have very high dimensional Q, that becomes a slightly subtle definition, okay? So, but it's just the right thing to do. If you base change from something flat, that's what you get. So, and then C is actually a nodal curve. We haven't asked C to be a nodal curve, right? That comes from log smoothness. And then locally on C, we have these three kinds of points, and I'm trying to be very consistent with my notation. So I always use little q for nodes, little p for these points that have an additional n, marked points, although we haven't labeled them. Feel free to label them or not, okay? They're both versions of Gromov-Witten theory. Typically one labels them. Here in log geometry, of course, they are a priori not labeled. But they are just there. If you talk about these log smooth morphisms, you just get them. And then we have generic points, eta, which and then is also the same as general points. So all points that are not P or Q. And at generic points, you just get the morphism is strict, so you just get the stuff from the base. At a marked point, you get an additional n. And at Q, it's slightly complicated, okay? The correct way to write it is a fibered sum, where you have an additional, oops, there's an n squared. You have an additional n squared, but you divide out this relation where an element q, this is part of the data, okay, is equivalent to 0,11. That was this element. So for the case before, where capital Q was the natural numbers, it was just 1. So the little q is 1. But in general, that you base change, right, and get some higher dimensional base. It can be any element q. I changed it. Yes, yes, yes. While writing it, I noticed. Sorry. Thanks. That is a row. Yes. Yeah. So the row. Yeah. Too many q's. Yeah, so this row was 1, and now you get an additional row in your base monoid capital Q that tells you how the node smoothes depending on which direction you go on the base, okay? Even at a log point. There's also a universal case. So any of these situations come from pulling back via a morphism from N to R to Q. And the R is the number of nodes of C. So this kind of turns this rho into a universal kind of diagonal thing. So I'll show it in a second. So the interpretation of this is a log structure induced from the total space of the semi-universal deformation of C. So probably all know that if you have a nodal curve, you look at the versal deformation. It's unobstructed. You get a whatever dimensional space, smooth space, but it has a number of divisors in there, which is the critical locus, the set of critical values. And it's a normal crossings divisor in the smooth space, and has as many components as you have nodes. And over each component, one of the nodes does not smooth. Okay? So this is what I try to draw here no, let me first say this. So the interpretation is that if you look at the semi-universal deformation of your curve, you have a smooth space, smooth total space, smooth base, with normal crossings divisors. You have a normal crossings divisor on the base, and the pre-image is also a normal crossings divisor. So that's, again, a log-smooth morphism torial pairs. And the induced log structure you can restrict to the central fiber, and that's what this universal thing is. Specifically, if you're in a stable situation, that's actually the log structure you get from the Deligne-Mumford modelized space and the corresponding universal curve over it. And there are actually, by the way, interesting applications to the geometry and topology of the modular space of stable curves using log geometry, exactly from this kind of story I'm telling you here. So I've tried to draw this for R equals 2. Okay, not sure how successful I was. So here's your two nodal curve, central fiber, and then you have these two divisors. So it has two smoothing parameters, T1 and T2. So the local equation here would be Z times W equals T1, and here it would be Z times W equals T2. So if T1 is 0, so along this kind of thing, that means this node doesn't smooth, and similarly for T2. And then you can see the log structure. So at general points, it's just this N to R that you get from the base. I didn't have marked points here, but if you had, you get an additional N. And then at the ith node, you get an N to R direct sum N squared, where this maps the row we had before, just maps 1 to EI. Yeah, at the QI's node. You have R nodes, and at each node, it's different, right? So you don't, for each node, you get one row. Okay, so I have 6 minutes if I'm right. Okay, so the ith coordinate captures the smoothing parameter of the ith node. Then this is what I said about stable cases. And it also comes with a universal property. Namely, so we have this universal curve. Whenever you give me a nodal curve, it comes with a universal log smooth structure over this spec N to R to C, over this thick log point. And there's a unique morphism to any other log smooth structure given by any monoid. So this EI would map to rho I.
You haven't imposed any stability on the curves?
No, no stability, no stability. Okay, so I have 5 minutes to start talking about topologization of log smooth curves. So that's a very cool story that is interesting independently of log Gromov-Witten theory. There's a lot of, this gives applications to this topology of the moduli space of curves. And there's a lot of work in this direction. So let's start over the standard log point. So here's my curve of the standard log point. I tropicalize. So here was the question, tropicalization is functorial. So obviously I get a diagram, sigma c to tau. The tropicalization of the space is just a ray. Okay? And that's a cone complex, the sigma c. And actually, we can see this very, very easily. We can reduce dimension by 1 because it's all cones. It's a map of cones. Let's take this distinguished point 1 in the base. The fiber over this is now not a cone complex, but a polyhedral complex, a one-dimensional polyhedral complex, okay? So this is this gamma, and once you have gamma, you can reproduce a sigma c by taking the cone over it. So here I've tried to draw this picture. So the most interesting case that kind of tells you everything what's going on is to understand what's going on at a node. Well, we need also mark points, but let's look at the node. So that's a little bit of a dense slide. So here's our monoid, and there is some nn squared. We are over the standard log point. So this is just given by this rho equal k, some number k. That is kind of interesting, so let's keep it. I just don't just want to talk about k equal 1. So this monoid, I claim, we had this before, right? So it's generated by 3 elements, namely 1, 0, 0, which is a row, 0, 1, and k comma minus 1. And here's written these kind of isomorphisms and its inverse, if you don't believe me, okay? So this is the sigma dual that you get, and it is isomorphic to this kind of fibered sum. So maybe we don't waste time in understanding this properly, but this is the cone you get. It has 2 generalization maps, which are these phase projections. So that's the projection along that phase. There's a projection along this phase. I call them chi1 and chi2. And these are the corresponding kind of fibers of M bar at the 2 branches at the node. So these are that's what I wrote here. So now we need to dualize. Let me make this a little smaller so you can just compare the two pictures, and then I'll zoom out again or zoom in again. So the perp of this guy is that lower thing. The perp of that is a very steep line here, spanned by 1k and 1, 0. Okay. The inclusion of rho in here is dual to this projection. Yeah, so tropicalization is functorial, covariantly functorial. Yeah, these kind of stocks of sheaves is covariant, but this is contravariant and this is covariant. So we get this kind of map. This is a dualization. This is a typical map, the typical picture that you get from a node of a log smooth curve over a standard log point. Okay, so you get this steep thing, you get a projection down, and you see the fiber over 1 is an interval of length k. It has k plus 1 integral points. So this is this pi trop inverse of 1. The vertices, this one and that one, these are the branches of C at Q. Aha. Now you see what's going on. So the gamma that we wrote down is actually a dual intersection graph of your curve C. It has 1 point, 1 vertex for each irreducible component, and one edge for each node. We also get something, so this is just that pi trop is dual to this map to rho. That's what I've said before. So what is the situation on mark point? It's a little easier, right? So the rho now is at the boundary. We still get a projection, but being at the boundary means that the corresponding fiber over 1 becomes unbounded. So it's an unbounded ray. So we see that gamma is the dual graph of C. So the vertices correspond to irreducible components, the bounded edges to the nodes, and the unbounded edges to marked points. You also notice, let's look at this picture again, that all of these are integral morphisms, so morphisms of cones, of rational polyhedral cones that preserves the integral structure. So you see that these edges that you get also have an integral affine structure, so an integral length function, a metric if you want, okay? So we get a metric graph with edges, bounded edges of integral length. Of course, then there are also unbounded edges corresponding to these marked points. So the slogan is the tropicalization of a log smooth curve over a standard log point is a metric graph with bounded edges of integral length k, corresponding to nodes with local model xy equals t to k, and unbounded edges corresponding to the other logarithmically special points, these marked points. So then there's a little more about what's happening in higher dimensions. Just one more slide, but maybe it's a good time to stop here, and I'll recap this tomorrow before we then move on to log Gromov-Witten theory.